Welcome back to ScienceClic. Today, electromagnetic waves. Imagine a particle that has an electric charge. Due to its charge, the particle generates an electric field around it. This electric field is static. It does not vary over time because the charge is motionless. Imagine now that we accelerate this charge. As it accelerates, the particle acquires a certain speed. According to special relativity, this speed leads to the appearance of a magnetic field around it. The electric and magnetic fields are intimately linked. They are two components of one same object, the electromagnetic field, and they will therefore interact with each other. In particular, the magnetic field which has just appeared will disturb the electric field. This disturbance of the electric field will in turn disturb the magnetic field. Step by step, the electric and magnetic fields will influence each other and vary in turn through this mutual disturbance process. The movement that has been imposed on the particle will propagate throughout space, spreading at the speed of light through the electric and magnetic fields. This phenomenon is called an electromagnetic wave. Depending on the acceleration of the particle, the electromagnetic wave will be more or less energetic. Waves can thus be classified into several categories of energy, depending on the frequency at which they oscillate. We find, of course, visible light with the different colors of the rainbow, but not only that. Infrared, ultraviolet, microwaves, X-rays, radio waves, or gamma rays. All these waves that we cannot see with our bare eyes are also electromagnetic waves. The vast majority of this radiation is invisible to us, but thanks to current technologies, we can design special cameras and instruments to detect them, or even emit them. This is what is used for microwave ovens, telecommunications, and other remote transmission systems, but also in astronomy and space telescopes. Astronomers observe the universe with different types of waves because this allows them to get a much broader and more detailed image of the cosmos compared with only using visible light. Electromagnetic waves are present everywhere. As soon as charged particles move, change speed or direction, they generate such waves. Moreover, all objects that have a temperature emit such radiation. To understand, it is necessary to look at the microscopic scale. The temperature of an object corresponds to the agitation of its atoms. Atoms are made up of two parts: a nucleus of positive electrical charge and a cloud of electrons of negative charge. When vibrating, the atoms shake their electron clouds. These behave somewhat as if they were connected by a rubber band. All these electrical charges are therefore constantly accelerating and changing direction. The atoms will thus emit electromagnetic waves, which become more energetic as the temperature of the object rises. The human body, for example, whose temperature is around 37 degrees Celsius, is constantly emitting infrared radiation. These waves are not visible to our eyes. We cannot see other humans glowing, but we can detect them with thermal imaging cameras. A very interesting feature of electromagnetic waves is their polarization. As we have seen previously, electron clouds in atoms behave as if they were connected to the nucleus by a rubber band. When atoms are agitated, electron clouds vibrate around nuclei in all directions, and the waves that are generated have a very chaotic shape. This type of wave is said to be non-polarized. Imagine sending a wave of this shape onto a charged particle. The particle will undergo a force because it interacts with the electric and magnetic fields that make up the wave. It will start to vibrate like the wave, and therefore like the atoms which produced it. It is in this way, for instance, that the sun can warm the Earth's atmosphere despite being millions of kilometers away. Its heat is transmitted from its surface via electromagnetic waves through the vacuum of space. However, it is possible to make atoms vibrate in a much more controlled way. The electron clouds can vibrate in one of three possible ways. Let's imagine a marble placed on a table and which is connected to a nail using a very tight rubber band. Let's imagine now that we launch the marble. We observe that its trajectory will most often form ellipses and sometimes either straight lines or perfect circles. Within atoms, electron clouds are attracted to the nucleus in the same way that the marble is attracted to the nail. Thus, they will also vibrate in one of these three possible ways, and generate very clean electromagnetic waves, which are said to be polarized, with either rectilinear, elliptical, or circular polarization. Radio antennas, for instance, cause atoms to oscillate along the axis of the antenna. They thus generate very clean waves with a rectilinear polarization. The polarization of light is not directly visible to the naked eye. Our eyes are only sensitive to light intensity, but not to the direction of the fields. Nonetheless, this is a crucial property which influences how light interacts with objects. In particular, there exist filters that can absorb certain polarizations. These filters are called polarizers. They are used for 3D cinema technology in particular, where it is possible to project two images simultaneously with two different polarizations, and to design glasses with polarizing lenses which will only let one of the two polarizations pass. Finally, as electromagnetic waves are waves, they evolve in space in accordance to very specific principles. Like all waves, they add on to each other. If we superimpose two crests, we will obtain a crest twice as high, whereas if we superimpose a wave with its exact opposite, the two will cancel out perfectly. This first principle of wave superposition is called interference. Wave interference is notably the cause of diffraction, which is observed when a wave encounters a small obstacle or passes through a very narrow slit. As we saw previously, when it moves through a transparent medium made up of atoms, an electromagnetic wave generates a force on the electron clouds, so as to set them in motion. These vibrations within the atoms will themselves emit waves, which propagate in all directions and which share roughly the same characteristics as the initial wave. Thus, even if we send light from a specific direction, the medium diffuses it in all directions. This is called scattering. The Earth's atmosphere is a very good example to illustrate scattering. The atmosphere itself doesn't really have a color. The sun, however, constantly sends electromagnetic radiation towards our planet, and in particular white light, which is made up of all the colors of the rainbow. As these waves pass, the atoms that make up the air vibrate, and thus scatter light in all directions. This phenomenon is as powerful as the wave is energetic. Red, yellow, and green colors correspond to relatively weak waves, while bluish tints have more energy. As such, it is the blue waves that make electrons vibrate the most, and therefore scatter light. That's why the sky is blue. Finally, when we send an electromagnetic wave on a material, for instance water, part of the wave continues its path through the material, while another part bounces back. We say that the wave is partly refracted and partly reflected. Let's start by looking at the phenomenon of reflection. If we shine light on a conductive material, like the metal of a mirror, some electrons on the surface are not bound to atoms. This is what gives the metal its ability to conduct electricity. As the light wave passes, the electromagnetic fields will set these free electrons in motion. Electric currents appear on the surface, and these currents perfectly reproduce the shape of the incident wave. The movements of the electrons on the surface will in turn generate a wave similar to the incident wave, but which propagates on both sides of the surface. This wave corresponds to the reflected wave. When we look at ourselves in a mirror, it is this wave generated by the electric currents in the metal that we see. On the bottom, the wave generated by the electric current is perfectly opposite to the incident wave. The two therefore interfere, cancelling out the initial wave. Following on from this, we see that the portion of the wave that managed to cross the surface of the water oddly seems to propagate in a slightly different direction and to move more slowly. This is called refraction. Refraction is a complex phenomenon which is due once again to the superposition of several waves. As the incident wave passes, the atoms and their electron clouds start to vibrate in the water so as to emit new waves which add on to the initial wave. But these new waves are slightly offset from the incident wave, thus slowing down the light beam as a whole. It is important to understand that the speed of light in itself has not changed. The electromagnetic field always reacts at the same speed, and each of the waves generated by the atoms travels at the speed of light. The light beam, however, which is the sum of all the waves, does slow down due to all these interferences. A beam of light therefore propagates more slowly in certain materials than in a vacuum, and it is possible for particles to exceed the speed of light, or rather the propagation of a light wave within a material. Just like the bang that occurs when an airplane exceeds the speed of sound, this phenomenon results in the appearance of a flash of light. This is the Cherenkov effect. It is a method currently used by scientists to detect neutrinos.